Hi, everyone. Thank you very much for coming. This is my first ever conference talk, so I'm very excited to be here, and I hope you'll find it interesting. Event-driven architectures and event sorting are not a new thing. However, they regain traction these days in the cloud era as traditional architectures such as CRUD-based applications are becoming more difficult to scale and manage in a distributed environment. My name is Amitay, and I'm a software engineer at Wix. I'm into functional programming, distributed systems, testing, and exploring new programming languages and technology stacks. Like I mentioned, I'm working at this awesome company called Wix, and we create a platform that allows our users to create beautiful websites. This is actually a real website from one of our users. He has an online store for selling unicorn adoption kits. Don't ask me what that is, but it exists, so you can check it out. It's very cool. We have over 120 million users, 2,100 employees, out of which 700 engineers and over 600 microservices running in production. Our engineering teams are spread across various locations in Lithuania, Ukraine, and Israel, and we have an amazing R&D center right here in Kiev. So check out our booth outside afterwards. So I want to share with you my story with event sourcing. And before we do that, I need to explain what event sourcing actually is. I will describe Eventim, which is a library we wrote as an infrastructure for event source systems at Wix, and what were the challenges we faced after running in production for about 2.5 years. Then I will give a quick intro about Kafka and Kafka Streams, which is a stream processing library which is written on top of Apache Kafka. And finally, we'll demonstrate how it all fits together and how you can create a reactive event source system using Kafka Streams as the backbone. But first, some background. Our story begins back in 2015, where we were asked to create a new service as part of Wix's CRM suite, which is called Wix Invoices. Wix Invoices is meant to help business owners to manage their invoices, send them to their customers, and receive payments online. Now, it doesn't sound like a very exciting field, but actually this has a quite interesting and complex domain model, which contains a lot of pieces of data and life cycle phases. And since we're dealing with payments and taxes and revenues, auditing must be heavily integrated into the product for ensuring the integrity of our customers' data. For example, this is the invoice details page. So we can see we need the business information here. We also need the customer information and other information related to the invoice itself, like the line items and tax information on which we perform various calculations. Now, this isn't too bad when we're viewing a single invoice. However, when we want to display a list of all invoices, and we want to give the ability for doing searching and filtering and sorting, and we want to display all sorts of aggregations for reports and stats, and this view also captures other information like payment events and page views. So we decided to implement Wix Invoices using event sourcing. So let's start by describing what event sourcing is. I won't get into too much detail here because this is a very big topic and there is much to say about it. And we already had in this conference great talk about it. For example, Idan's talk from yesterday. If you didn't attend it, I highly recommend checking out the recording afterwards. So the obvious solution for dealing with such a problem is just create a normalized schema in a relational database. This is how we used to work, and this is a method that has proven itself successful for many years, and it has really nice advantages in terms of data integrity and consistency. But as the schema evolves, the queries become more and more complex, and you need to join many tables together in order to satisfy them. So you can't keep your domain model aligned with your DB tables for long, and if you want to model your data based on your data persistence, you're going to have a bad time eventually. This problem is called the object-relational impedance mismatch. So the basic idea with event sourcing is quite simple. Rather than saving a mutable state in database and updating it in place, we save the succession of events that brought us to this stage. We can always derive current state by replaying all the events from the beginning of time. In functional programming terms, this is called the left fold over the event stream. This method has many advantages and benefits, since we're not overwriting our data, but merely accumulate facts about what happened in our domain. The big advantage here that we don't need to decide in advance what the queries we're gonna need, and model our data with this bias, which might be wrong or change over time. And we can always project the event stream to whatever query you're gonna need after the fact, which give us great flexibility. I'm sorry in advance that all the code samples will be in Scala, even though it's a Scala conference, but I'm sure you'll be able to pick them up. Okay, so let's take, for example, the life cycle of an invoice and how it will develop over time. So an invoice is first created, and we can see below the derived state of that event. And over time, for example, a line item is added, another line item is added, a line item is removed, we send the invoice to the customer, and we receive payment. So we can project the state from any point in time, and we can create the queries and reduce the complexity of the reads quite dramatically if we would have done it using traditional methods. This brings us to Eventim, the actual implementation we created for Wix invoices. We had several design goals when we started out the project. We wanted it to keep the library small and simple and non-intrusive. We wanted to maintain data integrity, meaning we don't want to save events that violates any business invariants. And we added the ability to easily add custom views, because we had lots of read models, and we wanted the views to be quick and fast. So Eventim is actually split into two parts. We have the write path and the read path. Let's start with the write path. So we have the user interface. This is just your regular browser. It will create a command JSON and push it to the server. And the first thing we do is decode the command JSON. This is the point where we can create simple validations on the payload itself. These are not yet validations that relate to the business rules. This will check, for example, for empty strings or numbers in range, etc. Then we have a command object. We can pass it to the command dispatcher. The command dispatcher holds inside it several command handlers. Each handler can handle a certain command, and the command dispatcher finds the handler that can deal with this specific command and pass the command to this handler. Up until this point, this has nothing to do with event sourcing, but one type of command handler we have is the event sourced command handler. So the event sourced command handler takes the command. The first thing it does is load the current aggregate. The aggregate is the domain object, in this case, the invoice. This will usually get done just by loading the events from the event store and rebuilding the current state. And once we have the current state and the command, we can derive what are the needed events that the command will produce. If the command is invalid, we can reject it at this point and not produce any events. So if we did create events, we have a new state of the aggregate. We can validate everything is fine and publish the events back to the event store. We use optimistic login to ensure that no concurrent writes are taking place. And once we save the events in the event store, we can acknowledge back to the client that the command was executed. And we also publish these events to an event bus. This basically ends the write path. So the read path, we have the events coming into the event bus. And we can attach several event handlers on this event bus. So one event handler will be a view projector, which means it will read in the events and update some persistent view. For example, a flat table in a database, which is already denormalized, or Elasticsearch index, or whatever you need in order to satisfy your read needs. But you can also add another event handler, for example, for sending emails or generating reports. But once you have your denormalized view, you can easily have your user interface query against it very efficiently. So this is really high-level overview of Eventim, but we had some pain points along the way. And despite of the simple design, the library became quite big. This architecture has inherent eventual consistency, because it takes time until the view gets updated. This is a conscious decision we've made to sacrifice strong consistency in order to achieve better performance, but this is not correctly integrated into the product, and there are many situations where the client performs read after write. For example, create a new invoice, then reloads the invoices list, and the new invoice is not there. Most of the time it's fast enough that you won't notice it, but there are times it will not update fast enough, and this will compromise the user experience. But I think the biggest challenge we had was actually rebuilding the views, which is quite a complex operation and involves many different moving parts. And I'll try to explain why this is complex. So from the right side, it's quite easy to add a new event handler that will listen on the event stream. But if you just subscribe a new event handler and it starts listening on a live system, you can just handle the events and write them to the database, because they might rely on past data being there. So you must ensure that all past data was already written before you can handle the new event coming in. And we have a similar problem from the right side. If we add a new event handler, but no events coming in to trigger the view rebuild, and the view will already try to query this database, and we don't have any data in there. So we created a mechanism to handle with these problems, but like I said, it was quite complex and not easy to do in a distributed environment where events are coming from various servers, and it was quite complicated. So this brings us to Kafka. The problems I described brought me to search for alternative architectures. We wanted to keep the benefits of event sourcing, but with simpler ways of dealing with inconsistencies and rebuilding views. Let's see a quick show of hands. How many of you are using Kafka in production? Okay, I'd say about 1/4. Keep your hands up if you ever used like stream processing applications like Kafka Streams or other. Okay, cool. So Kafka basically is a distributed append-only log. It's most often used as a queue or a pub subsystem, but as we'll see, it can do much more. And it's a really battle-tested technology, being used at really high-scale companies and proving itself worthy of dealing with really high load. So the basic abstraction Kafka gives us is a topic. This is basically a logical queue. It is partitioned, meaning a queue will divide its messages across multiple partitions which are configured. And producers will push messages to each partition depending on the key of the message. The important thing to notice here that the order is maintained within a single partition. So if you need to keep ordering, you need to produce the message with the same key. Now, after you have these messages produced in a queue, you can then consume it. Kafka keeps for each topic a retention policy, which is also configurable, so you can tell it how long you want to keep the messages. This gives you great flexibility, because you can add consumers that will replay all messages that already happened. You don't lose messages once they are consumed. And you can add additional nodes to what's called a consumer group, which is basically just one logical consumer, but you can scale it up to multiple nodes. So the Kafka will handle the balancing of which node handles which partitions. So if one consumer can't keep up, you can simply add another node to the consumer group, and Kafka will do its magic and rebalance everything. And like I said, because this is the partitioning model that Kafka uses, so you still get the ordering guarantees per partition. This is a real high-level overview of Kafka. Kafka Streams is a library also by Apache Kafka that is meant to do stream processing on top of Kafka. And it uses two main abstractions, which are the streams and tables. So streams, you can think of it as data in flight. These are unbounded, continuously updating data sets, which means it starts somewhere, but it never ends. It's like an infinite collection. And because it's ordered replayable sequence of key value pairs, this makes it sound interesting for an event source system. Tables, on the other hand, you can think of them as data at rest. This is what the data looks like at a specific point in time. And if another message comes with the same key, it will override the previous one. So like you know from a database. One important observation to notice is that we have sort of a stream-to-table duality. Basically, they are the same, two sides of the same coin. So let's see an example. You can take a table and stream all changes to the table. So now you turn this table into a stream. But you can take this stream and materialize it back into a table. This is how databases replicate and persist their data internally, but it's not visible to you. So let's see a real example. This is, for example, a user that shows page views, a table that shows page views per user. So we start with Alice with one page view, and this table develops over time. And we see that each change can be streamed back to create these key value pairs. And we can materialize back this stream into the table and get the same table back. So this is one thing to notice. Another key ingredient we want from any stream processing application is the ability to do stream transformations. So we're used to doing these transformations in the small. If you use Scala 8 collections or Java 8 streams or Scala's collections, you can take a collection and do, for example, map or filter or flat map or other operations and get a new collection out of it. But the ability to do this in the large on streams which are infinite and you don't know if they'll ever end, so this is really nice ability to have, and you declare these transformation really, really nice programmatically and declaratively. Another thing you can do is take two streams and join them to a third stream. So this basically takes the messages from both of the streams and push them to a new stream that contains all the messages. A less obvious thing you can do is take a stream and a table and join them together. This is possible because we talked about this duality between a stream and a table. But also this is an interesting transformation to make. So Kafka Streams give us the ability to create stream processing apps that will transform and enrich your data. It will support stateless and stateful operations. Stateless, for example, the mapping and filtering we saw, and stateful if you need some sort of aggregations. It supports windowing operations for dealing with time windows. This is a really strong feature. I won't talk about it too much, but we'll see an example afterwards. And the cool thing is it's embedded inside your app. You don't need to deploy a separate cluster for doing this processing. You just use the library as a jar inside your application, and all transformation happens inside your app. So you get also the properties of elasticity and scalability from Kafka itself, because everything relies on Kafka. So in order to define your stream processing app, what you need to do is basically tell it where Kafka is. This is a bootstrap service config. And you need to tell it your application ID. By giving it an application ID, this will use Kafka's consumer group mechanism, and you're able to scale out your application by just deploying new servers with the same application ID, and Kafka will automatically distribute the load. So let's take a closer look what each of these stream processing apps look like. What you basically need to do is define your processor topology. The topology is basically just a graph of transformation. You define each of the nodes and how they are connected together, and you have two special kinds of nodes. These are the source processor and the sink processor. Most of the times these will be from just Kafka topics. You'll read in information for Kafka topics and push downstream information back to Kafka topics, but you have other options as well. And you see here we have several stateless operations like the mapping and filtering, but we also have joins that which are stateful. For this, Kafka Stream uses what's called the state store. This is how Kafka internally saves local state on the machine itself. By default, it uses RocksDB, but you can plug in other backends for that. And it uses Kafka itself for replicating these state stores, so they're also resilient. So how do you define each of these nodes? You have several options. The most basic one is the processor API. This is the most low level, so most of the time you probably won't gonna need it. But it's worth mentioning that all standard operations like map and filter are using this API to define these operations. So if you need very custom processing logic, you can use it. My personal favorite is the Streams DSL, which lets you programmatically describe your topology. And let's see a quick example of how that looks. So the first thing we need is a streams builder. And now we create a stream from the topic text lines. This will give us a stream that will update every time a new message comes into this topic. Now we can take these text lines, flat map the values by splitting each line into words. So we had a stream of text lines, now we have a stream of words. Now we can group this stream by the word, and we get a table. And we can count each values per key and materialize it as a state store, which is called count store. And later we can take this table and transform it back to a stream and push it to a new Kafka topic. So we had a topic of text lines, and we created a topic of word counts. Yeah, so we have another option which is called KSQL. This is an SQL dialect for streaming data. It's more high level. This example shows you how you can create a table with possible fraud attempts by selecting authorization attempts for the same number that had more than 3 attempts within 5 seconds. So this shows you an example of the time windows capabilities I talked about. And it shows you how concise it is to define really complex semantics. So it's really nice. So let's see how we can use these tools to create a simplified invoices app on top of Kafka Streams. So high-level design again. We have the user interface, and we have a node server, and our Kafka cluster. So the user interface will publish a command, a create command to the node server, and all it will do is push a command to Kafka. At this point, we can acknowledge that the command was accepted, and sometime in the future it will be processed. So we have a stream processing application which will handle these commands. And once the processing is done, it can push back the result to a different channel, different topic, sorry. Now the node server can listen on the topic and push live updates to the clients using a WebSocket. So we also have here inherent eventual consistency, like we had in EventNim, but this is where we embrace it rather than ignore it, and really take advantage of the async nature of the system. So we can create another stream application, which is a projector, which its job is to project the events into some view, which the server can just read straight from the view. And like we said, because this is Kafka Streams, we can easily scale up or down as much as we need each part of the system. So let's take a deeper dive and see how these command handlers are, these stream processing apps are implemented. So we'll start off with a command handler. Like I said, the first thing we do is listen on the command stream. So we take each command and need to map it to some result, transform each command into a result. The result is either the command succeeded or failed. So for that, we need to read the current state of the aggregate. So we have a state store that keeps a snapshot of each invoice. And now we can decide whether this command is valid or not, and we can create the failed or succeeded result. This result will be pushed back to command's result topic. And for successful results, we'll produce events. So we can flat map these successful results into the events will be pushed downstream to the events topic. We can later listen on that event stream and aggregate it to update the state store. And it's also useful to push the snapshots to its own topic, because why not? Now, all of this command handler in Logic is just 60 lines of Scala code. So again, you get a lot of benefits and really concise and declarative way. So let's take, for example, a closer look on how this node is implemented, how we aggregate the events into snapshots. So this is basically the code. We take a stream from the invoice events topic. We group it by key, which is the invoice ID. And then we aggregate it, giving it a function for doing the aggregation itself. And we materialize the aggregated table into the state store, which is called snapshot store. All right, the projector is even simpler. We just listen on the snapshots stream. We map each snapshot, which is the current state of the invoice, to how the record will look like in the database. And then for each record, we persist it. We just save it. And we can push it again downstream to a new topic, which contains how the records look like in the database. So we get this architecture where Kafka is in the middle of all. And we have small microservices talking to Kafka. For example, the invoice just takes commands from the Kafka cluster and pushes back information back to Kafka. And we can have other microservices that communicate the same way with themselves amongst other microservices. And we can easily push information into Kafka, for example, changes in inventory, or get information back from Kafka, like producing analytic reports. So this gives us really decoupled, a nice architecture, which is really scalable. So what did we gain by using this design compared to Eventim? Like I said, this is very simple and declarative. Eventual consistency is handled gracefully, and we embrace it. And it's very easy to add or change custom views. And obviously, we got all the benefits we had with event sourcing, plus the scalability and fault tolerance properties that Kafka provides us. So now let's see a quick demo. I'll mirror the displays. So I'll start the command handler. And I'll start the projector. Just a second. It's gonna Thanks. Yeah, live demos, you know. Yeah, dead demos. Let's try that again. Okay. Let's try that again. Okay, so the command handler. Running. Okay, so it doesn't work, but you know, live demos. But I have this prepared yesterday as a video, so less exciting, but let's see it. Okay, so this is, imagine I'm doing it like live now, starting the command handler and starting the projector like I told you. Now I have this UI for displaying the list of invoices. This is just sample data, and I create some invoices. You see the little lag I have there between the command, the time it's accepted until it's acknowledged and processed. So because I'm pushing the changes back to the client, I can open another client and create invoices from that client, and everything will sync up magically with WebSockets. And if you issue invalid commands, you also will see the result that the command is not valid with a reason. And another nice property, you can just kill your command handler altogether. And if you try to create a new invoice at this state, it will just hang, nothing happens. But the command was already sent to Kafka. So if I bring back the command handler back again and wait a while, it will pick up where it left off, and the command will be processed, and you see it got updated. Wow, live demos, wow. All right. So let's get back to the slides. So we saw that already, demo. Okay, so what are the takeaways? Event-driven systems and event sourcing can help build very flexible and scalable systems. But you should always know your trade-offs regarding consistency guarantees and schema evolution and data integrity. And Kafka Streams are powerful tools that can be employed in many use cases. So that's basically what I have for you, so stream on. Here are some resources, including the demo code which will hopefully work for you, and some other information. And we have actually quite a lot of time for Q&A, so if you have any questions.
Hey, thanks for the talk. You mentioned there is a state store, right? So is it persistent? I didn't quite get that. And is the Kafka feature or Kafka Streams feature, or it's your own stuff?
Which one?
A state store.
Yeah, so state store are an internal part of Kafka Streams. Each time you do some stateful operation, like aggregating or joining, these are not things that can take a value and return a value right away. You need to keep some data persisted. So Kafka uses state store to do this persistence. They are saved locally to disk on the machine that does the transformation, but it's also replicated via Kafka itself using special internal topics to other nodes. So you can lose this node and you won't lose any data. So yeah, it's a Kafka Streams feature. And you can plug and play the internal backend of the persistence layer. So the default is RocksDB, but you can use other custom state stores if you need them.
Okay, thanks.
Thank you for the talk. It was nice. In which way should we handle errors during Kafka streaming? Either by any reasons, or we got invalid message, or we can't send a message to this destination topic?
You mean how do you handle invalid messages coming into the queue?
Handling any errors during streaming.
Okay, so like you'd handle errors in any other application, you need to catch exceptions, because the Streams application will shut down if it has an exception. So you need to make sure that exceptions are handled. And if you have, for example, different message types pushed into your topic and you can't handle them, this is where Kafka is using what's called the SERDA. It's how Kafka uses serialization and deserialization. So you can use, for example, a protobuf or Avro, which are tools for handling with schema evolution with your messages. So this way, if an invalid message comes, it will you'll know how to handle with it.
Is it possible? Thank you for your presentation. So, is it possible to receive duplicates of events. For example, if the consumer handler dies.
Yeah, so regarding delivery guarantees, this is also configurable in Kafka Streams. You can define what semantics you need, whether it be at most once, at least once, or exactly once. Now, the exactly once comes with a caveat because you have to make sure all your processing is idempotent, because there are stuff that are not possible to do exactly once. But Kafka will run the entire stream processing topology and push all messages downstream. You can think of it as a single transaction. So it handles all this. All this is handled for you by Kafka Streams, and for each message that comes into your topology, everything must be finished before the next one can be processed.
Thank you for the great talk. And my question is about distributed group by. For example, you have some map operation, and then you have a group by on your stream by some new key. And you need, actually, for this, you need a shuffle, some kind of shuffle operation. You need to move data with the same key to node, to be to the same node, to be aggregated. How does Kafka Stream handle this? And what happens if some of this node fails, for example?
So basically, all operations are using Kafka's partitioning model to distribute the load. So if you do an operation which preserves the key, for example, if you're just mutating the, mapping over the value, for example, this will stay in the same partition and you can handle it in the same node. If you change your key, obviously you need to push it to a different partition. So this is basically the partition model is how Kafka handles with this. So it's distributed across the partitions.
Yeah, but the question who need to handle this repartitioning? So how we need to push this mapped data and with new key to another Kafka topic, or we or Kafka Streams handle this by
Kafka Streams
itself?
handle it for you. Like we saw in the code examples, the code you need to write is very declarative, and the library does all this this work for you.
Okay, thank you.
Yes, my question is, so we have a very simple use case. We have a data publisher, yes, data publisher, and a data processor. And we have some error, for example, database error, when processing some event. So can we skip this message and leave it in our queue, in our topic, and return to processing after 5 seconds, for example?
Let me see if I understand your question. If, for example, your database is down, so you can't update it, but you want to process this message?
Yes, and so we need to repeat. We need to repeat some operation after, for example, 5 or 20 seconds. So can we leave leave message in this topic? And
okay, so Kafka topics are configured with retention policies. So messages are not lost once they are processed. You can define how much time it will take for them to be deleted. It's a matter of trade-off between how much storage you want to invest in it and how important the messages are for you. So in such a case, if your processor fails, and for example your database down and an exception is thrown, when you start it, it will remember its position and will try to pick up from there. It will not skip this message. If you want to handle it explicitly, you can catch this exception and for example, create some kind of retry mechanism with your own semantics, but yeah, you have to handle it somehow. But the messages are not lost. That's the important part. So you can always go back to messages and reprocess them.
So I should save this event to retry mechanism in another topic.
That's a possibility, yeah, depending on your product needs.
Okay, thank you.
Hello. What about committable source? It supports?
Pardon?
Committable source.
I didn't understand that, sorry.
I connect to Kafka over stream, and if I process message, I commit manually to Kafka.
Oh, whether you control the commit?
Committable, yeah.
Oh, so like I said,
like Akka committable source.
So I'm not too familiar with Akka, but I talked about the delivery guarantees that you need to configure. So again, the library handles this for you, and it will make sure that the message is fully processed inside your topology before it will consume the next message. So you need to define whether you need the semantics of at least once, exactly once, or at most once. So this is tunable regarding your needs.
Thanks.
So, what do you actually use for event store?
Pardon?
What do you actually use for event store?
Yeah, so it seems strange to some people because we didn't see any database that holds the events, but you can think of Kafka itself as a sort of database because it already has the durability and fault tolerance and replication. So if you define your topic with a retention policy of keep the events forever, so it's basically, it acts like a database. If it's really important for you, for example, to perform various queries on the events afterwards, you can always add a new stream processor that will read the event stream and push them to some other database. But you don't have to. I mean, you can treat Kafka as a database in these cases. This is what I meant where it's not only a queue or pub subsystem. It can do much more.
Okay, so you actually can configure Kafka to do not delete all data at all.
Yeah.
Okay, thank you.
Is there a possibility to support somehow distributed transactions with Kafka Streams?
Yeah, so since version 0.10, I think, Kafka added this feature for creating distributed transactions where you can commit messages to different partitions transactionally and safely. And when you enable the exactly once property in Kafka Streams, this will internally use this transaction mechanism for this. So yeah.
Okay, thanks.
Hi, I have some questions. For example, we have two topics and create, and we have a window with 5 minutes, and we want to join these two topics into other topic using Kafka Stream, but with not by key, but by two fields. Is it possible? And for example, should we create a new topic, a key topic with needed key, and only then join this two field, two topic in other?
When you join two streams, you choose the function that takes the key and the value from the first one and the second one, and then you can choose by what you want to join. So, but you might again lose the key for the partitioning. So
yeah, but we want to join not by key, but by some field which we have in a message in a topic.
But this function, this object will let you also not just look at the key, but also the value. You get the values from both topics, and you can decide whether you want to join what you want to join on. So if I remember correctly, you can do that. Whether you want this or by transferring to a different topic with a key and then joining, again, it depends on your needs and your ordering semantics. So, okay, thank you very much.